Okay.
Okay, just continue. Our next speaker is, sorry, before that announcement, before lunch today, we're going to make the conference photo, and we're going to be here in the garden, so be prepared for the photo in 45 minutes. Okay, so now our next speaker is Verde-Star from Universidad Autónoma Metropolitana. He's going to talk about uniform parametrization of the recurrence coefficients of Q polynomial sequences and the q-Askey scheme. Please.
Well, thank you. Well, I want to thank the organizers for inviting me to be here, and I'm very happy to be in this event to honor Natig. And I'm going to talk about some results that I obtained by using a matrix approach to orthogonal polynomials in general. And it is related to Q orthogonal polynomials. And I thank Renato for giving a very nice overview of what the Q orthogonal polynomials are, because then I don't have to spend any time explaining the basic definitions. Okay. The idea is that I'm going to explain a few things about the q-Askey scheme. Then I describe an extension, and this is done by means of explicit formulas for the recurrent coefficients in terms of zeros and poles. And give some examples of some probably new sequences of Q orthogonal polynomials. Some of them are not mentioned in the q-Askey scheme. I don't know if they are included in the NU scheme or the Han table. So there's a lot of work to be done regarding the new examples. Okay. The q-Askey scheme is described by a table of things that I'm going to show next. And those are the polynomials that satisfy Q difference equations either on the Q linear lattice or on some other lattices. And there are 29 families included there. And the idea is that each family is described by means of some parametrization. The problem is that different families have different parameters, and it's not easy to go from one family to another one. Usually you have to make some substitutions of parameters and then take some limits as some of the parameters go to 0 or to infinity or to something else. And we are going to define a new class of polynomial sequences using the three-term recurrence relation, this one here. So I'm going to describe how the alphas and the betas are defined. And here I'm putting 1 in the coefficient of pk plus 1. So my Jacobi matrix has 1s on the upper diagonal. So the q-Askey scheme is describing this table. Well, you don't have to read all the names. It's not important now. And it has Askey-Wilson and Q-Raka polynomials on top. And then you can go from those two families, go down to other families by taking some limits or substitutions. And there are 5 levels here. So what I'm going to show you is a new definition, a new parametrization that includes all of them with one single parametrization. So that will be a family that will go there on top of those. Okay. The original way in which I found this family was using matrices, infinite matrices. And what I did is I found first explicit formulas for the initial terms in the recurrence relation. That is, I found that the alphas and the betas can be described in terms of the initial alpha 1 and beta 0, 1, and 2. And if we know those 4 parameters, we can get all the others for the first for the classical Q orthogonal polynomials, and then for an extended family that I defined using matrices. So the new result is that we can construct the alphas and the betas in a different way using explicit formulas. This is the initial construction. We start with rational functions. The first one is a rational function in x. The variable is x, and y, and d1, d2, and d3 are complex parameters, complex numbers. This is the numerator is a polynomial of degree 8, and the denominator is also degree 8. And then I define another rational function, this one here. It's simple, it has degree 2 in numerator and denominator. And I found that there's an alternative version of the second function that it works okay if this parameter y is not 0. And it's essentially interchanging k1 and k2. Those two are constants that depend on the parameters y and the d's. So these are just two constants to simplify the expressions. Okay. So if some conditions are satisfied for the rational functions, for example, that if we substitute x by q to the k, we should not get 0 here, then we can define the sequences alpha k and sigma k, this form, but sigmas are related to the betas because they are the sums of the betas. So the idea is that if we have a polynomial sequence that satisfies the 3-term recurrence relation using this sequence alphas, and one of the sequences obtained from either this formula or this formula, then we can include those families, those sequences in the extended class of q-orthogonal polynomials that I call the extended Q-hand class. So those are all the sequences that satisfy this 3-term relation, recursive relation, using some of the sequences defined with the alphas and sigmas before. The betas are just the differences, sigma k minus 1, or with the other sequences. And I use the sigmas because they have an easier formula for as a rational function, easier than the betas. Okay. If one of the dj's, one of the parameters is 0, then the corresponding polynomial sequence is a classical q-orthogonal family. So they satisfy a second-order q-difference equation in the linear lattice. Okay. And what happens here is that this new family contains all the sequences in the q-Askey scheme and some others that may be new. And this is the reference that Renato mentioned a couple of times. It's just the Encyclopedia of the hypergeometric orthogonal polynomials. So we have checked all the examples in the last chapter of this book. Those are all the most general Q orthogonal polynomials in the q-Askey scheme, and just giving values to the parameters and substituting in the rational functions, or sometimes it's easier to work with the reverse functions to deal with zeros and poles at infinity. So we get all the sequences, including Askey-Wilson and Raka, and Q-Raka. Okay, so let's say a few things about the rational functions. It's convenient to represent the parameter y as the square of something, as p squared, and q as the square of r. Because if we want to describe the roots of the polynomial of the rational function u, we have these 8 numbers, and the poles are p, that is a double root, minus p, so another double root, and p times r with plus or minus sign, and p over r, and minus p over r. So that's why I'm using y and q as the square of something. So it's easier to describe the zeros and poles. And those zeros and poles determine everything, and they satisfy an important kind of symmetry relation. If the parameter p is not 0, then the zeros and poles are invariant on the map that sends complex number z to p squared over c. You can see that here. Like you can pair all the zeros, like 1 with p, d1 with p squared over d1, and so on. And the same thing happens with the poles. So they satisfy kind of symmetry with respect to inversion in the complex plane. Like you consider the circle of radius probably is p squared, and inversion with respect to that circle leaves the zeros and poles invariant. Okay. In general, we have 2 possible sequences for the sigmas, but they coincide in many cases. So I'm not going to say very much about the alternative sequence, what I call the alternative sequence is sigma k. Okay. And if we give values to the parameters, we can get some cancellations of zeros and poles. So the degrees of the numerator and denominator of u of x can be certain numbers, not every possible pair. Let's use this notation. Degree of u is the pair nm. M is the degree of numerator, m is the degree of the denominator. And as I said, not every pair of values is possible because of the cancellation happens by pairs, cancellation of zeros and poles. So we can use the pair of degrees as a way to classify the sequences, the polynomial sequences that correspond to a given set of parameters. And we do that, and we can compare the sequences that we can get using the giving values to the parameters and the examples in the q-Askey scheme. And I hope you can see the difference with the red red little squares are the examples in the ASCII scheme in the book that I mentioned. And the blue ones are the new ones. Some of them are not positive definite. And maybe a couple of them need the use of complex numbers. So,
what are the coordinates?
Excuse me?
Number of poles and number of zeros. What are the coordinates?
The pairs of degrees of poles and zeros. I'm using this notation. And m as the degrees of the numerator and denominator. Okay? So, for example, this one here, that's the 8, that corresponds to Askey-Wilson and q-Raka. So that's the top in the q-Askey scheme. And if we go down, then we can go all the way down to 0, 0. Those correspond to Chebyshev polynomial sequences. And for example, this will be 3, 4. This point here, this is the numerator and the denominator. Okay. So there are a few examples that may be new, and probably I have not checked, but the ones that Renato mentioned should appear here somewhere. The new ones. For example, if we give these values to the parameters, written here in terms of T1, T2, and so on, using the description in the book for the Askey-Wilson polynomials in terms of the coefficients of the recurrence relation, they are described by means of these parameters. So this choice of the parameters P and the D1, D2, and so on produces exactly the Askey-Wilson polynomials, normalized in the usual way. If we we try to invert this relationship, what we get is this. We can go from the T's to the P and D's in this form, but the D's appear in the denominators. So if one of the D's is 0, we cannot find the T's. Okay? So if we start with Askey-Wilson and we want to get some sequence that corresponds to parameters where one of the D's is 0, we cannot do it. Okay? So it's not possible to just do a direct substitution of parameters in Askey-Wilson to get the ones that I can get through with the P's and D's. Well, I already said that. Another example, if we take those values for the parameters, we get the q-Raka polynomials. So it's a direct substitution. There are no limits here. Another example, with these values, we get a constant sequence for the alphas and a constant sequence for the sigmas or the betas. And those correspond to some family of Chebyshev polynomials, normalized in some way. The other family of the same kind is obtained with this choice of parameters. Like, I think this is something like, well, they are both Gegenbauer polynomials, but one of those is Chebyshev normalized in some way. Another example is this one. Here we have the degrees of the alphas are 4 and 4. Those are, remember that the alphas are rational functions of q to the k, And so in this case, this has degree 4, and this one too, degree 4 and 4. And these are the sigmas that correspond to those alphas.
But in this Chebyshev case, R corresponds to what? Because Chebyshev
What?
polynomials, they do not have any parameter, right? But in your scheme, R will be surviving, or what?
No, R is no. No, R is the square root of Q.
Ah, okay.
Okay?
But Chebyshev, they do not depend on Q, right?
No, but what this means is that there must be some way to represent Chebyshev polynomials as well, to describe them as q-orthogonal polynomials. So I can get them by just giving values to the parameters. Okay?
You have degree 0 over degree 0.
No, okay.
Yes.
Sorry?
You have degree 0 over degree 0. which is
Degrees.
on Q.
Yes. Yes.
You are not mentioning Q Chebyshev polynomial, because there are some now Q extension Chebyshev.
No, those are the usual Chebyshev. Yeah, the classical Chebyshev polynomials included here.
Okay.
So I get them just by giving values to the parameters. Okay? Okay. And in some cases, it's convenient to consider the reversion of the rational functions. In this way, we can just deal with zeros, poles and zeros at infinity just by direct substitution of those values in the reverse functions. Okay. So that's the main idea of this work. Okay. The references are here. I started working on this subject in this year, 2013, and I have a couple of papers where I describe the matrix approach to orthogonal polynomials, and the new results are in this preprint in the archive that you can see here. Okay, in the time that I still have for this talk, I'm going to explain a little bit how the formulas were obtained. So it's not, they were not obtained by looking at special cases and then trying to find a generalization. So they appear as a natural result in working with matrices. Okay. The idea of the matrix approach is that we consider a polynomial sequence as a matrix. So if we have a sequence of polynomials, the coefficients a and k are considered as the elements of an infinite matrix, and this is defined in this form, and it becomes an invertible lower triangular infinite matrix where each polynomial corresponds to a row of the matrix. So that's the basic idea. And therefore, the polynomial sequences become matrices, and then they are of the same kind of objects as the operators that send polynomials to polynomials. And we can, for example, describe the multiplication by x will be a matrix. The recurrence relation will be described by this matrix, and the orthogonality is described in terms of matrices in this form. So the rows of A are orthogonal if they satisfy this equation for some matrix of this form. So that's the three-term recurrence relation. The Q-difference operator is this one. And we have here the definition of the Q-hand class. This is not the, no, this is wrong. This is the extent, this is in my notation for the extended class. There's a mistake here. This will be just the Q-Han class, the classical. And yes, I made some mechanical substitutions, so this is not the extended class, so the classical class. Okay. And so the definition is the usual one. A sequence of Q orthogonal polynomials is in the Q-Han class if the difference of the sequence is also orthogonal. So the usual definition. And this is my version of the characterization of the classical Q-Han class. It is done in terms of the Jacobi matrices of the sequence. L is the Jacobi matrix of the sequence of polynomials, and M is the Jacobi matrix of the sequence of the differences of the polynomials. If they are both orthogonal to polynomials, the sequence and the sequence of differences, then they must satisfy this equation. The Jacobi matrices must satisfy this quadratic equation in L and M, and it involves also the matrix of the Q operator. So when I found this, I tried to see which sequences I could identify in the q-Askey scheme, and I found that some of them were included, well, all the classical ones, but some of those were not included, so I decided to modify the equation and to extend the class, and it can be done this way. Instead of putting 0 in this side, I put a multiple t of the difference operator, and it works. So now the sequences that have Jacobi matrices L and M for the differences that satisfy this equation belong to a larger class of sequences, and it turns out that it is large enough to contain all the elements in the q-Askey scheme. And from this matrix equation, we can find explicit formulas for the alphas and the betas in terms of the initial ones. Here, this one, alpha 1 and beta 0, 1, and 2. And the parameter t enters in the formulas for the alphas only. The betas are independent of t. Okay, I'm going to show you the formulas for the recurrence coefficients that are obtained this way. The q integers are defined the usual way, and the sigmas are the sums of the betas. And I define a few auxiliary constants just to simplify the writing of the expressions. So the parameters become the initial terms in the recurrence coefficients, alpha 1 and beta 0, 1, and 2, and the new parameter t. This is a new auxiliary function that contains powers of q, and these two constants, h1 and h2, that are defined here. So this is just things for the simplification of the notation. And then for the sigmas, I have this formula. You can see that it is a polynomial of degree 2 in q to the n. There's a q to the n here, and there's another one here. And the g is also g is a polynomial in q to the n, so this is of degree 2 also. And for the alphas, I got a more complicated formula. That's why I use the auxiliary constants, the h1 and so on, and the function g. So this is the formula, and it is possible to determine the degree of the numerator and the denominator, and it is 8 and 8 as the maximum. So those are the formulas, and you can see that they depend essentially on, as I said before, the parameters are this, t and the initial coefficients. So if you want to find the recurrence coefficients of a sequence in this class, you just find the initial ones, and from those you can reconstruct all the others using these formulas. Well, but the problem is that the usual description of the families in the q-Askey scheme are done in terms of other parameters, not using the initial recurrence coefficients. So I decided to look for a change in the description of these two functions. They are rational functions of q to the n. So I decided, well, let's try to find the factorization of numerator and denominator. For the denominator of the alphas, is not difficult to find the general formula as a polynomial in q to the n. For the numerator, it was more difficult, but using Maple, it was possible to do it. And the nice thing is that the roots of the numerator appear by pairs. And that's what made it possible to find the factorization of numerator and denominator. And for most of the choices of the arbitrary parameters with alpha not 0, we can get an orthogonal sequence in this extended class. It's not for every possible choices, because there are some choices for the betas that produce some alpha, like alpha 3 equals 0 or alpha 6 equals 0. That means that we have to eliminate some, maybe some hyperplanes in the four-dimensional space where the alphas become 0. Some of the alphas become 0, so those are not acceptable. And from these formulas, we can also get the formulas for the all the ingredients in the q-difference operator of Bochner type that are satisfied by the sequences when they satisfy a difference equation on the linear lattice. And we checked all the elements in all the sequences in the Askey scheme, and they appear, they can be obtained by giving values to the initial terms. Well, we can also deal with the examples that satisfy the equation on the quadratic lattice. They also are obtained this way. Well, I'm going to skip this. This is just the kind of problems we can. Well, this is what I solved using the factorization. Okay, I think that's all. Okay. Yes.
Luis, can you please go back to the page with the Askey scheme?
Sure.
Because I need that to explain my question.
I stop.
Very good. It is well known that in ASCII scheme, when you put at the sum level one of the parameters 0, then you go down, right? So you can consequently go down, right?
Yes.
Yeah, it's well known. But recently what we did actually, we showed that you can reverse this. So you can start with the lowest level and define some attachment procedure at one parameter and you go up. So we proved that we took this way on the left side, started with continuous pyramid, go to continuous big pyramid, go to Al-Salam Chihara, and go continuous Q-Han and reach Askey-Wilson.
Yes. Yes.
By attaching one parameter at each time.
Why not at Askey-Wilson?
Sorry?
Then why do you stop at Askey-Wilson? Can you
I will answer that question. Presumably your parameterization with all parameters 0 correspond to the case continuous pyramid. Is that correct?
Yes, I think so.
Right.
Yes.
So can you also formulate some type of procedure which also enables you to go from all zeros to y non-zero, and then y and one more, and so step by step to go up. Can you do that?
Well, I think so, because in my description, you don't have to take any limits, just substitution.
No,
Okay.
but I am not using now limits also.
No, yes, I know, but so
I'm speaking about going up. Not
yes, but the going up is just moving in the four-dimensional space of the parameters. So my description is general. So you have a point in four dimensions.
But this description also general. But our idea was that at each level, polynomials were defined by different scientists, by different ideas.
Yes.
But our way of looking at that is that they could actually simply start with the pyramids.
Oh, yes, yes.
And then do not invent Askey-Wilson, but go up to Askey-Wilson.
Yes, you can do it. Yes, yes, it is possible.
Also in your procedure.
I think I can do it. Yes,
Okay.
yes. It will be just one particular path from one point to another one.
Right.
Okay. So the nice thing is that with my general formula, I can just give values to the parameters and go here or go here and go down and in any way, just by direct substitution. Okay. So.
Go down, it's clear.
No, but it's not. There's no direction in my parameter space. You can go from one point to another one. If it means going up or down, it just corresponds to what are the degrees of the numerator and denominator. So that's here you can also. There's a correspondence. If you go down, the degrees of the alphas are going down from 8 and on top to 1 I think is here, or 2 1 in some of these. I don't remember the numbers, but where is here? So these are the different cases. 8 is Askey-Wilson and Raka, and there are some examples that have lower degree in the numerator here, 5, 6, and 7. So and going down here is just producing some cancellation between zeros and poles. Okay, so that's what I did to find the possible new cases. Just choose the parameters to produce some cancellations and go down to 0, 0. Okay. Yes.
I'm very enthusiastic about this your piece of work, but for a reason which you probably do not expect, which is there's a very strong correlation to work by Sakai in 2001. Sakai is a Japanese guy who found the most general elliptic discrete Faraday equation, which is a nonlinear equation above the classical second-order nonlinear equation of Faraday found in 1900. But I'm afraid not so many people in this audience are living in the nonlinear world. So I have the feeling that your construction, which is really beautiful, is exactly the linear restriction of a result by Grammaticos and Ramadi in 2010, probably in JPhys A, Journal of Physics A. I have a precise reference with it.
Oh, I would like to know about it. Yes.
And in their construction, they have two coordinates, let's say y and z, yn, zn. And they define a nonlinear q-discrete equation, which is yn minus 1 times zn plus 1 equals rational function with 8 zeros and 8 poles of yn or zn, and similar for the second component. So I'm absolutely confident there is a strong correlation between their work and their work.
Okay, thanks.
I have a few other comments. You mentioned 29 possibilities for your first slide.
No, those are just the families that appear in the ASCII scheme. Those rectangles in this diagram. Where is it? Here.
Yes.
Those.
This 29 should be 24. As a consequence of the result of the Japanese school 2001.
Okay. Well, yes. I suppose that if you
mentioned that 29 could not be final because there are some complex relations between.
yes.
Some of them could be identical. So my statement, my guess, is not my guess at all, is that this 29 should be 24 as shown by the Japanese school by considering cubic curves.
Yes, but that may be because if you find a different parametrization, maybe you can put together two similar families. Like
but in the Q-Hunter tableau, they are not repeating. In the Q-Hunter tableau, they are not a repetition. It could be in the nonlinear lattice. In the Q-Hunter tableau, the one that appear in the ASCII scheme are, they are no repetition. They are, you cannot get from one the other one in a trivial way. You know what I mean?
no, but
I'm not sure.
In the Q-Hunter tableau. No, I am sure because it's coming from the difference equations.
Look about transformation which concern nonlinear stuff.
But this depends what you can get from one to another. For example, getting from q to q minus 1. But then this is not trivial in the equation. You know what I mean? From the point of view of the equation, if you fix the lattice, you have no choice.
I have a final question. How many parameters in your construction? 4 parameters.
yes.
So you have to upgrade to 2 more just to fit the Japanese scheme. So 1 more for Q discrete and 1 more for elliptic discrete. And that will be just gorgeous.
Thanks.
Manuel,
Yes.
may I answer? I promised to answer to the question.
No problem.
The point is, you asked me why we didn't go higher, right?
Yes.
The point is that it's well known that at least there is belief that only up to the ASCII we still have so-called beautiful bispectral properties, right? You know that. So we decided that we will probably can get higher, but we will lose these bispectral properties. So that was the reason why we started.
Any more comments? Questions? Well, let's thank Luis again for the talk.